Hello, everyone. Welcome to today's live broadcast, Expanding Analytical Horizons and Efficiencies in Geoscience, Petrochemical, and Environmental Research. I'm Laura Bush, the Editorial Director of Spectroscopy, and I'll be your moderator for today's event. We're delighted to bring you this educational web seminar presented by Spectroscopy and sponsored by Milestone. Over 20,000 customers worldwide use Milestone's products for microwave acid digestion and solvent extraction, synthesis, and ashing, as well as acid purification systems and direct mercury analyzers for solid, liquid, and gas samples. Their consultative partnership approach and the trust of their customers have led to Milestone's becoming an industry expert in a wide variety of applications involving some of the most challenging matrices. Milestone's mission is to enable laboratories worldwide with success, growth, and continuous innovation. We have a few housekeeping announcements before we get started. The webcast is designed to be interactive, so we encourage you to ask questions. You can submit questions at any time by typing them in the Q&A box, which you can find on the right-hand side of your screen. You can enlarge the slide window by clicking on the small green icon in the upper right-hand corner, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the webcast. And if you have any technical problems viewing or hearing the presentation, please click on the question mark help widget in the dock at the bottom of your window. I would now like to introduce today's speakers. We are very pleased to be joined today by John F. Casey, Giulio Colnaghi, and Jonathan Talbott. John F. Casey is a professor in the Geology Department at the University of Houston in the Earth and Atmospheric Sciences Department. He serves as the director of a university core facility, the Center for Advanced Analytical Geochemistry. He previously served as department chairman from 1999 to 2012. He has worked in the field of trace element and isotopic geochemistry of terrestrial and marine geological materials since the early 1980s. He's the author of more than 100 peer-reviewed articles in the geosciences. Giulio Colnaghi started working with Milestone in 2003 as an applications chemist. He has developed methods in partnership with analytical laboratories in government, academic, and contract sectors, as well as contributed to scientific publications on microwave sample preparation. He now acts as a country manager for the SRL team. Jonathan Talbott is an ICP-MS applications engineer with Agilent Technologies and has over 20 years of ICP-MS experience in both applications and technical sales support. John has worked for Varian for 5 years prior to joining Agilent through the acquisition of Varian in 2010. His areas of expertise include speciation, clinical applications, and 21 CFR 11 compliance for Agilent ICP-MS systems. Thank you all for joining us today. Dr. Casey, you have the floor.
Thank you. Well, good morning from the University of Houston. And today we're going to talk about a couple of applications that we've been working on for digestion and analysis of crude oils and other types of refined oils. And then we're going to also talk about our basic work on rock and mineral digestion using the single reaction chamber microwave system, the ultrawave by Milestone. And again, we're using the triple quad ICP-MS for our trace element analyses. We're going to try to demonstrate the ease of use and the improvements in sample preparation with the single reaction chamber microwave for both these applications. And in particular for the rock application, we'll try to demonstrate recoveries of even refractory minerals like zircons in our analysis. The advantages in microwave digestions for us and the attractiveness was that basically it would reduce the sample preparation steps and processing times. It would enable us to do the sample digestion part preparation of our preparation to less than 1 to 2 hours, and that's coming down from anywhere from 12 hours to 7 days, depending on the applications of the digestions we undertake. And typically we undertake those in the past with mixed acid bomb digestions. I'll go over that in a minute. And then the further advantage is the potential that the analyst can basically load the sample and leave during the process of digestion, so saving time in the lab. This has kind of been the gold standard for the geochemical community and digestions of complex matrices, and these are Parr Bombs, and there's an insert in the Parr Bomb, a 23 milliliter Teflon cup, which we place the sample with strong acids, and usually those strong acids involve hydrofluoric and aqua regia mixtures of various amounts depending on the application, and then they're placed in ovens, conventional ovens at somewhere between 120 to 150 degrees and sometimes even higher, but generally there's a limit on the temperature we can heat, and again 12 hours to 7 days depending on what type of rock or material we're digesting. The assembly of each bomb is also time consuming, so all these are time consuming steps in the digestion process. The Parr Bombs really have served the geochemical community very well over many years. But our question when the single reaction chamber microwave came out, is there a better way to do these digestions? Can we go to higher temperatures and pressures during the digestion? Can we achieve better seals, because the Parr Bombs sometimes don't seal or we lose sample? And then can we achieve more rapid throughput in our sample preparation and maybe even cleaner chemistry? These pictures show the progression of use of a Parr Bomb, especially in our digestions of crude oils. We have kind of a rapid point to wind up with a very corroded Parr Bomb, and in a trace metal lab, that's not a very satisfactory looking vessel to digest our samples in. So the major challenges for us in the geochemical area is complete sample dissolution for any materials, but especially for rocks and rock powders or sediment powders that are inhibited by refractory minerals such as zircon. I'll show you some of these zircons in a minute. And then some materials have very low abundances. So our crude oil analyses are dealing with very low abundances of trace elements that we're trying to document. So we're always pushing the limits of detection and quantitation. And then some materials are really high in organic matter, and those organic matrices present challenges for the ICP-MS. So we have to find some way to destroy those and those organic matrices. And then some materials have a very wide range of elemental abundances, presenting challenges on how many instruments we need to do a complete trace element fingerprint of a rock or a crude oil, for example. So here are the culprits in the rock digestion game, and these are zircon crystals, and you can see the top figure shows nice clean crystals, and then the bottom figures show a little bit more complex zircons. The more complex zircons turn out to be easier to digest. The nice clean crystals are a little bit harder. This just shows a crystal with radiation damage, but these refractory minerals are also concentrating certain trace elements we want to recover in the digestion process. So zircons contain heavy rare earths, they contain hafnium, uranium, and other elements, as well as zirconium, which is a trace element in these rocks. So complete recovery of these refractory minerals are important in our rock digestions. But they require very aggressive digestion procedures involving hydrofluoric and aqua regia mixtures, and typically we've done this in these Parr Bombs, as I said, and dissolving anywhere from about 100 milligrams to 250 milligrams of sample. There have been microwave digestion attempts in the past, and some of them have proved successful, others have not, but this has generally dissuaded the community from going the microwave route. the problem is that there's not a guarantee of complete digestion with the microwave system. I'll give you an example. This is just a paper by Taylor et al. In 2002 in which they digested a fairly easy sample for us. We can do this on a hot plate of basalt. We can do it on a hot plate. And they got good recovery of things like zirconium and hafnium on this mafic sample that's listed on the left-hand side of this table. And if you look at zirconium, the reported material in the standard was 108, and they recovered 95, so that's pretty good, parts per million. And then for hafnium, 3.76 on the reported, and they recovered 3.93. But if you go to rocks that contain a lot of zircons, like a granite, they found a different result. So the reported value in the granite in the middle here of the table is 300 parts per million. They only recovered 39. For hafnium, the reported value was 7.9, and they only recovered 0.87 in their digestion. So that's been the problem. Other microwave tests have proven successful for basaltic material, but again, for material that contains zircons, it's more difficult. So our procedure starts with clean reagents. So we have a kind of an elaborate ultra-pure water system, which starts with deionization and then moves through a Barnstead system and then a polishing system with a millicue. And the other part of the clean reagents is the acids. We doubly distill all our acids. We use the Milestone subclean system, which will handle hydrofluoric, nitric, and HCl that we use in our digestions. So this is the single reaction chamber microwave digestion system, and you can see it features this single stainless steel pressurized vessel that's in the middle of that counter there, and the samples are lowered into multiple samples can be lowered into that chamber. It's critical for us to have low procedural blanks. The way the system works is the samples are put in these tubes with the mixture of clean acid. And then if you look at the lower right-hand side of the diagram, the samples tubes are lowered down into this reaction chamber, which is lined with Teflon to handle the strong HF acid digestions that we do. And then the chamber is pre-pressurized with an inert gas so that there's no boiling of the acids possible. And then the microwave energy is applied. The digestion is done in about anywhere from an hour to 90 minutes. And then there's a rapid cooling step, step 5, and then automatically the samples come to the counter surface after the digestion. This just shows you a picture on the left. Upper is the sample holder that's lowered down into the chamber. The Teflon liner to the stainless steel chamber holds the base load, which is a weak nitric acid load. So that forms fluid around the samples, and the microwave is acting on the fluid and heating the fluid, not necessarily the sample in the tube. And here's just on the right here, and you can see the single reaction cell that the samples get lowered into. There's a temperature probe that you can see on the cap of the cell. The cell is clamped by these two stainless steel clamps and then sealed. We also have the option of using various sample sizes because there are multiple sample holders. So for crude oils, we're either using the 4 or 5 sample holder, and we're using quartz tubes to prevent burning through the Teflon. So basically 0.6 grams or 0.4 grams of oil can be loaded into each one of those vials, and then we use the 15 holder for rock samples because we're only dealing with 100 milligrams of sample. So for crude oils, I'll go over crude oils first, and then we'll go into rock digestion. The typical methods used in industry are what we call dilute and shoot methods, where a solvent is diluting the oil, and then that mixture is directly introduced into the ICP front end. Another sample preparation technique is emulsions with water. Both these first two result in really high dilution factors, which can limit both the detection and quantitation limits that we're getting on particular analytes. So we don't like those two methods very much, although they're heavily used in the industry. Ashing followed by strong acid dissolution. We've never been able to get good recovery with these ashing techniques. We've done lots of tests, but the recovery for our analyte targets is not very good. So we basically use a strong acid mineralization technique, and we used to use these Parr Bombs, but now we strictly moved to the ultrawave because it does a much better job. In terms of open and closed systems, the ultrawave operates a little bit differently in that the sample chamber is closed and sealed, but the pressure on the outside of the sample vessel and the sample chamber pressure is exactly the same and kept that way through the digestion. So these are all the ASTM approved methods for trace element analysis in crude oils, and you can see most of them are dilute and shoot methods, and they result in a limited analyte set in general. So the first one for crude oil results in 4 elements. So we're trying to expand these kinds of methods, and we've expanded them to about 57 elements that we routinely analyze for in crude oils. These are more advanced techniques. They're more on the research side usually rather than routine, but you can see that they produce relatively higher numbers of element lists because ICP-MS technology instead of just ICP-OES technology is involved in analyzing the crude oils. And you can see the best results in terms of analyte numbers were achieved with these microwave acid digestions, so 25 in one case and 28 in the other. That always doesn't mean that you achieve quantitation with these methods, but it showed us that microwave digestion was a way to go on this. So this is what we do. We load the sample into the quartz tube, and then we react it for a while with peroxide, and then we add the strong acid mixture in of aqua regia. The sample is lowered into that sample chamber and digested, and the results when we pick up the sample are these greenish-looking fluids, and you can see some of the CO2 in the upper part of the test tube. We take those test tubes over to a hood and let them degas, and we wind up with a clear solution that you can see on the right-hand side. So that's a clear aqueous solution, which we can use aqueous standards on in a routine ICP-MS analysis. So trace elements have their uses in the petroleum industry at all levels, from upstream exploration to production. We're working with geochemical allocation models for with the trace elements, so that's involving production. Basic research studies of oils involve trace elements, and also the refineries need to know their feedstocks in terms of their trace element content. So many of the trace metals act as catalyst poisons, and it gets very expensive if they don't know what they're feeding into the refinery. And so in the refining process and catalytic cracking, this is very important. And other metals cause corrosion in the refinery that can lead to high maintenance costs. Environmentally as well, regulatory compliance for things like lead and sulfur abundances in fuel oils. More and more states are going to more stringent requirements for especially sulfur of late in their fuel oils. So this pretty much shows you the entire process. Loading the base load, which is in this Teflon vessel up in the upper left. then loading the sample holder in with the crude oils and the mixed acids, and then the digestion technique, and then finally a clear aqueous solution. Oops. This just shows our digestion procedure. So we're achieving digestion temperatures up around 260 degrees. So the red line is the preset temperature profile that we want. You can see we can monitor run pressure. We can set the maximum acceptable pressure and the maximum temperature of the outside of the reaction cell, so we can control the environment very well. With oils, you have the problem of occasional pressure surges, but this system handles those pressure surges very well. So you can see a little marked pressure surge with it where that arrow is. So we see the run pressure go up a little bit, but immediately the microwave power cuts down and controls the overall pressure of the run, and the temperature climbs at the prescribed rate till we get to 260 degrees. And then we have a cool down period that lasts about 10 minutes or so, and that's aided by a water chiller. So it's a pretty efficient way of digesting the oils. Then we take the oils to our laboratory where we have an Agilent 725 ICP-OES and an Agilent 8800 triple quad ICP-MS, and we analyze for the 57 trace elements. We pre-screen with the ICP-OES for the high abundance elements, and then we go to the Agilent triple quad for the very low abundance elements. So we achieve really great detection limits and quantitation limits for crude oils. We target elements with the ICP-OES that are high in abundance and low in abundance, the triple quad. And the advantages of the triple quad over the single quad that we also have are that basically we can start to mitigate many of the interferences that were problematical in the past with the single quad ICP-MS. So there are real advantages for the triple quad for analysis of crude oils. The instrument detection limits are much lower than the single quad ICP-MS, as you can see here. And we can remove or mitigate these polyatomic interferences, isobaric interferences, and the non-monocharge interferences. And this really helps in crude oils with low abundance crude oils where there's sulfur and phosphorus to quantify both of those elements. So with this combination of the digestion system and the triple quad ICP-MS, we're able to quantify oftentimes about 57 elements, between 55 and 57 elements, and these are the elements we can quantify in that digestion and analytical sequence. So in terms of recovery, we have to know our recovery. So we've analyzed the Coniston multi-element oil standard with multiple digestions and analysis, and these are our average result for 0.4 grams of that standard. So we recover 20 elements in that standard. Then we follow that up by a successful test with by doping a Coniston base oil for an extended suite of elements, 57 elements, and we achieve complete recovery as well with the digestion system. Here's a NIST fuel oil that we've been working with NIST on to basically create reference values for a wider suite of elements. If you look at most NIST standards, they only have a few elements that are certified. The certified elements are the ones with the red arrows on them. There's only 3 certified elements in this standard. They're denoted by these green dots with the red arrows, but there are other green dots where they provide reference or information values. They're not certified. So our basic goal was to show recoveries that were compatible with their certified values. and we've shown this average mean value in these black dots for the 57 elements that we've measured. And they're listed in terms of increasing RSDs for 10 analyses with 5 separate digestions. And basically, there are actually 10 analyses plotted there that you can't see because the RSDs are so low with this QQQ, so they're all superimposed on each other. The only place you can see maybe the 10 analyses is on the right-hand side of the diagram, where the lines, because of the poor precision for silver and tantalum, are actually showing. But otherwise, the repeatability is quite amazing with the triple quad ICP-MS. So here are our overall results for the first 3 elements that are certified. So we're at RSDs below about 4%. If you look at that middle column, and then the accuracy is less. We're within 10% on accuracy of all those elements. And typically, our RSDs are low for all of the reference values. We have some discrepancy in terms of arsenic and selenium, but we may be doing a better job. There was another study with the microwave that basically came up with the same results we came up with. One thing, I'll go back to that slide. There were 9 analytical techniques used by NIST to accomplish eight elements reported. We used 2, the ICP-OES and the triple quad ICP-MS, to quantify all of those, as well as all of the 57 elements. So this just shows a natural crude oil, 2 natural crude oils, a Sumatra crude oil and and a California crude oil, as well as a NIST crude oil in black. And basically, we can present these fingerprints of each one of the oils. This is on a log scale in parts per billion. So basically, these are very resolvable fingerprints, even though they're condensed on the log scale. The other thing I want to point out is that if we look at the range of elemental abundances we're measuring, it's all the way from major elements like sulfur, greater than 1 weight percent, down to PPT levels for the rare earths here. This is just an example of a 20 well oil field that we were able to fingerprint from the wellhead every oil with a separate fingerprint. And these kinds of analysis will let us do production allocation from each of the wells if we have a commingled oil, say in a pipeline coming from the field. So I think the bottom line in the oil studies is that we can produce very repeatable, high quality, high precision, and high accuracy trace element analysis with the digestion technique that we've outlined in the triple quad ICP-MS. So now I'll move ahead, and hopefully this will be short, but we'll move ahead to the rock powders. We have a 50-element suite that we analyze by strictly triple quad ICP-MS. Zircons are a problem in terms of our digest, so we've taken U.S. Geological Survey standard reference material, and we've taken 100 milligram of rock powder and tried to digest them in a single reaction chamber microwave system. Our results again produce high precision, accuracy, and repeatable measurement with the Agilent 8800 triple quad ICP-MS. The digestion times in the microwave is 90 minutes compared to 1 to 7 days in the Parr Bombs, so that's a big time saving for us. And then the single reaction or the standard reference material recovery database, I'll try to present a few of those results in the next minute or so. In particular, I want you to note the abundance recovery of zirconium and hafnium, which is really dependent on complete digestion of this refractory zircon mineral. I'll skip that slide. So this is just a profile of our digestion. So the digestion temperatures reach 250 degrees. We have control over the run pressure, and basically we're finished the digestion in about 90 minutes. We use hydrofluoric and aqua regia in our digest to digest the rock powders. And this is the standard reference material. These are easy digest. These are basaltic rocks. Again, the green represents the reference material reports, basically, and the black represents our analysis. And you can see that we're right on target for most of the elements for in our digestion. So we're recovering most of these elements fairly well. There are some elements here near the quantification limits of the triple quad, and they often show a poorer precision. If you look at the bottom diagram, this is just a comparison of the RSDs. So you can see the RSDs are well below 10% or 5% for most of the elements, except for those near the quantitation limit. And the light green represents our recovery. So if we look at zirconium on this one, it's 112%, and then hafnium 103%. So we're doing pretty well. These are basaltic samples. So basically, you can see this is another standard reference material, basaltic, and we're achieving about 100% recovery on just about every element on this one. And then these get into the rocks that could bear zircon. So these are andesitic rocks, where we have 107% recovery on zircon and 104 on hafnium. So we think we're doing pretty well. This is a shale, 99.3 recovery on zirconium and 97% on hafnium. This is a more difficult sample. It's a granite, and 294 parts per million zirconium. We're at 100% recovery on zirconium, and we're at 99% recovery on hafnium. And then even a more difficult rock, a granite diorite with over 600 parts per million zirconium. We're at 108% on zirconium recovery and 101% on hafnium recovery. And then finally, our most difficult sample is 1,308 parts per million zirconium. We're at 104%, if I'm reading that right, on zirconium, and 100.8% on recovery of hafnium. So I think we're doing pretty well. I'll skip that slide because of time. And then if you look at the overall zirconium recovery, we're generally within 90 to 100% on 13 of our reference samples. And if you look at the isolines for zirconium and hafnium, you can see we're doing pretty well in terms of the reference values in GRM and our measured values, and hafnium is almost a perfect one-to-one line. So I'm just going to go to the summary because of time here. Basically, our digestions with the single reaction microwave system has proven efficient for reducing time-consuming parts of our sample preparation procedure for both crude oils and rock powders. We seem to have solved the problematic refractory mineral problem in the digestions, at least of rock powders. The triple quad ICP-MS offers us better sensitivity and is better able to mitigate interferences that we have. And then we'll probably be able to further advance on this by doing more matrix matching on our efforts with the standard reference material. And also probably another factor that Jonathan will talk about is the increased sensitivity of the newer models, triple quad ICP-MS. So what's next for us is basically homogeneity tests, dissolving single zircons, and tests of isotopic ratio work. So I'll end there and hand it off to Jonathan, and thank you for your attention.
Actually, it's Giulio who will start.
Giulio, yeah.
Okay. Thank you very much, Dr. Casey, for your presentation. I would like to remind to everybody that you can find additional information about the information, the presentation Dr. Casey provide us on the spectroscopy of this month, where there is an article made by Professor Dr. Casey. So having said that, my name is Giulio Colnaghi, as Laura said, and I would like to take you through the Milestone tools for geological and petrochemical trace metal analysis. Whenever we talk about trace metal analysis, we have to take into account not only the ICP-MS, but all the steps that our sample has to go through to get to the solution and then to the analysis. So we have to prevent the contamination from the material we use. So the type of material we use becomes extremely important for trace metal analysis, as well as the kind of cleaning we perform on this material, the type of reagents, the quality of the reagents, as well as the environment where you perform your analysis. Clearly, in all these steps, an important part of the process is also the digestion, where you have to take care of getting complete digestion of your sample, but at the same time you have to make sure that you are not losing any elements like the volatile elements, or you are not losing any part of your sample. In addition, you like to get a digested solution which is free of interferences, and therefore you can get a better analysis by your ICP-MS. To perform this kind of all these kind of steps, Milestone offers a number of different tools. So we have available tools either for cleaning, for purifying acid, and as well as for digestion, as we have seen with Dr. Casey. I would like to give you a quick overview of what is available today from Milestone for cleaning your glassware, your vessel, your reactors for the digestion. Since few years, Milestone is active in the trace metal analysis with the Milestone Trace Clean. The Milestone Trace Clean is a unique system capable to clean your digestion vessel, your quartz tubes, your glassware using nitric acid in vapor phase. The capability of performing cleaning in vapor phase allows us to reach amazing cleaning performance and allow you to further reduce your blank and therefore to get better analysis whenever you work in traces. In addition to the trace clean, we have also developed two systems, the Duo Pure and the Sub Clean, which are fully dedicated to purify your reagent grade acid in order to get ultra pure acid. We all know that when we are talking about ICP-MS and when we talk about traces, the ultra-pure acid becomes a must. But we also know the cost involved in the purchasing of this acid and the consumption you have to do, you have of this acid. Therefore, Milestone has developed a sub-boiling system which is capable to purify reagent-grade acid by using infrared heating, by avoiding any boiling of the acid, and it evaporates only the surface of the acid in order to have a condensation of the ultra-pure acid into a PFA bottle. This generates a number of benefits for the user, since you are able to save up to 90% of the cost of the ultra-pure acid. Remember that we are starting from the reagent grade acid, so we completely cut the ultra-pure acid cost. We offer a greater productivity since the duopur is capable to produce up to 400 ml per hour of ultrapure acid. We are also able to have in our lab always ultrapure acid completely fresh. So we don't have a bottle of ultrapure acid sitting for weeks or months, but we have the capability to purify our reagent only when we need and in order to perform our digestion, dilution, or whatever is required in your laboratory. The duopur and the subclean are both suitable for purification of nitric acid and hydrochloric acid. The subclean is also capable to perform hydrofluoric purification since it is not using a quartz boiler but is using Teflon boiler. Having said that, we also talk about the challenges in sample preparation, especially when you talk about tricky samples like the geological and the petrochemical samples. I would like to take you through a couple of solutions that Milestone offers for this digestion. In particular, today we will be focused on the ultrawave. You have already seen a preview thanks to Dr. Casey, but let me spend a couple of words also on the Milestone Ethos app. The Milestone Ethos app is the latest revolution of the Milestone Ethos family. The Ethos family started early in the 90s, and we developed a number of units. The last Ethos app is not simply an improvement of the first generation, but is a completely redesigned system. As of today, the Ethos app offers much higher power, which allows us to have a very fast eating even of high throughput rotors. It is completely made in stainless steel, so it has a very robust construction, which assures long lifetime of the system, as well as safety. In addition, the new Ethos app has a larger microwave cavity. The main benefit of having a larger microwave cavity is that we can accommodate higher throughput rotors. As of today, Milestone offers a unique solution, which is the SK15, a 15-position high-pressure rotor, which is matching also the most challenging and reactive samples, like could be the geological as well as the petrochemical samples. But the SK15 also provide a great productivity since it's offering 15 position where you can perform multiple digestions during the day. But the Ethos app is also easy of use. We know how important to have a system very easy to use in order to simplify your life in the lab. So one of the crucial part of the digestion is the method development. We do not want you to spend time in method development, and therefore today you have access to built-in application libraries directly on the terminal, where you have over 300 methods that you can use, and therefore you don't need to develop any kind of application. In addition, the combination of our software along with our direct temperature sensor allow us to have a continuous temperature control during all the digestion. Whenever you think about organic samples, and in particular petroleum samples, you have to think about samples that are extremely reactive. Therefore, having a direct and continuous temperature control is a must to ensure a good digestion and full control of your temperature during all the run. Milestone also has been always an innovative company, and since we want to support our user as much as we can, we also developed the unique Milestone Connect. The Milestone Connect is a web-based application where our user can have access to an application support 24 hours, 7 days a week. So virtually there is no anymore requirement to perform any method development. All the application information are directly either on your terminal or on the Milestone Connect. But we also provide you tutorial videos, a huge library of scientific articles, and you can also control the system directly from your smartphone, from your tablet, or from your PC. So it's really an evolution of the conventional microwave technology. Having said that, there are a number of limitations in the conventional rotor-based technology, which we have to face when we do digestion of geological samples. So let's have a look to what are the geological samples and what are the challenges of digesting these samples. So if we consider samples like rocks, sediments, and so on, these are very complex metrics. Often they have completely different compositions, and they require a very aggressive acid mixture. Could be nitric and hydrochloric, could be many times also the use of hydrofluoric acid is required. The downside also of these geological samples is that they don't have a great solubility into the acid. Therefore, we have to play with the sample amount as well as with the acid volume. So if we look to this sample from the digestion point of view, what we need to get a complete digestion are two important points. One, we need a system capable to reach extremely high temperature. Dr. Casey was talking about 250 to 60, so very high temperature is required to get complete digestion. In addition, we also need to be able to maintain this temperature for a long time. This is another crucial part to get complete digestion. Of course, we don't need 12 hours or 7 days as it is normally required in the Parr Bomb, but we need to have a system capable to maintain the temperature for 1 hour, 90 minutes, and so on. When we look to the petrochemical samples, this is a completely different approach. They have a different need, but also in this case, we have a lot of challenges. The petrochemical samples are mainly organic. They are extremely reactive, so we have to take care of the reaction, of the exothermal reaction they develop during the decomposition. They are mostly digested with nitric acid, sometimes a mixture of nitric acid, peroxide, hydrochloric acid is sometimes used as well. And the digestion in this case requires not only high temperature but also high pressure capabilities. So the combination of the temperature and pressure capabilities is a must to achieve complete digestion of petrochemical samples, which was a very limiting factor in the past and in the conventional microwave system, and it is not in technology like the ultrawave. In addition to the temperature and pressure capabilities, we also need an accurate, precise, and quick temperature control. Remember, we are talking about oils which, when they compose, they have a very strong external reaction. So a slow temperature control or not a non-direct temperature control is going to strongly affect the control of my digestion and the quality of my digestion. Milestone has fought for a long time how to overcome all these challenges, and a few years ago we developed the Milestone Ultrawave, which is using a patented technology which is called SRC, Single Reaction Chamber. Let's have a look how the ultrawave and why the ultrawave can overcome these challenges. First of all, the ultrawave works in a completely different way compared to all conventional microwave. We have already seen this with Dr. Casey, but there is a single step that I want to underline, the step number 3, where we pre-pressurize the chamber before to start our microwave program. This allows us to work with very easy construction of the vials and allow us to overcome the problem of closing and opening all the vessels. All the other steps are done automatically by the system, so you have the microwave heating, and then at the end of the run, as we have seen, we have a fast cooling thanks to a water chiller, and then the system automatically releases the pressure. In addition to that, there is a big plus of the ultrawave that for the first time, we are able to control the temperature and the pressure in every position, and we are able to assure the same temperature and pressure even by working with completely different sample types and acid mixture. Since the parameter we set in terms of temperature and pressure are the parameter of the whole reactor, so of the big reactor, whatever is inside to the reactor, it will stay exactly at the same temperature and pressure that we set in our software. But the ultrawave give us the possibility to work at to exceed the conventional limitation of a digestion system. Why? Because the ultrawave provide higher temperature and pressure capabilities. We can digest any sample type in the same run, so we can do a rock along with the crude oil without dividing the sample in different runs. We can use also a much simpler, a much easier construction of the vials. So we move from vessel and rotor technology to racks and vials, where we can work either with quartz vials, Teflon vials, as well as with disposable glass tubes. The ultrawave, thanks to the way it works and its technology, also offer a much higher throughput than any other microwave system. And it is able to match the need of the petrochemical samples by digesting large sample amount thanks to its high pressure capability, and the need of the inorganic samples like the geological thanks to the high temperature capability. The ultrawave also strongly reduces your sample preparation cost, since it will completely cut the consumable cost, and it will allow you a higher productivity of your digestion process. But the ultrawave is also a more safe system, since it works with the stainless steel reactor and not with the plastic reactor. The ultrawave, as I said, is not working with rotors, but is working with racks. So the racks available are different, from 4 up to 22 positions. What you see here are just the 5 and the 15. The 5 position normally is used for large sample amount, while the 15 is used for routine analysis and for having a good throughput. Both racks are available with different vials material, from quartz up to disposable glass vials or Teflon vials. I would like to underline a bit why the geological samples can be done in a better way in the ultrawave. First of all, because the vessel construction of the ultrawave allows us to reach higher temperature and to maintain this temperature not for minutes but for hours. So the stainless steel construction of the reactor in the ultrawave allows us to work at 300 degrees and to maintain this temperature for a long time. Of course, we can use any type of vials, and this depends on the chemistry as well as on the type of analysis that you want to perform. In addition, we can use any type of chemistry. As well, we can control directly the temperature in all the positions. So the ultrawave assures us a higher temperature capability. We can hold this temperature for longer time, and we directly control the temperature, assuring a great digestion of all our geological samples. An example could be a digestion of one rock with 0.25 grams with a mixture that can be nitric, hydrochloric, and hydrofluoric acid, but we can even work at 280 degrees for 60 minutes, which is absolutely impossible with any other digestion system available in the market. If we look to the petroleum sample, to the petrochemical, clearly there are different needs, but still the high pressure and the high temperature capabilities of the ultrawave allow us to increase the sample amount that we can digest. So while in a conventional microwave we are very limited to low sample size, in the ultrawave we can go up to 0.5, 0.75, even 1 gram of sample according to the sample type. The ultrawave also has a much better temperature control, not only thanks to the temperature sensor, but to the base load that is loaded at the beginning of the run, which helps to reduce the exothermal reaction and control the exothermal reaction. The ultrawave is also much safer, as we have seen before, thanks to the ESS stainless steel reactor. And the quality of digestion we get from the ultrawave is extremely high by working at very high temperature and very high pressure. We are able to strongly reduce the residual carbon content in our digested solution. An example of the digestion could be half a gram of crude oil with nitric acid and hydrochloric. The working temperature in this case is normally around 260 degrees, but look at the pressure is over 150 bar. I hope I've been able to give you a nice overview of our solution. Feel free to contact us for any question, and now I give the word to my colleague from Agilent, Dr. Talbott.
Great, and this is Laura. I'll just step in a moment to say that we'll run just a few minutes past the top of the hour to give Dr. Talbott a chance to give his talk, and I think he may make it a little bit briefer. And I also just want to point out that I forgot to mention earlier that we have resources available from our sponsor that you can find in the green resource widget below the presentation window. And you can also find out more about Milestone on the web at milestonesrl.com. Dr. Talbott?
Thank you, Laura. The title of my presentation today is Put Your Results Beyond Doubt with the new Agilent 8900 ICP Triple Quadrupole ICP-MS. This coincides with Dr. Casey's presentation where he talked a lot about the 8900 and some of the capabilities of that. As you know, Agilent has been in the business of innovating in ICP-MS for about 30 years now. If you look at the center instrument there at the 7700, that was only introduced 7 years ago. And since then it has been supplanted by 4 other units. We have the triple quadrupole series on the top, and we have a continuation of the single quadrupole series down below with the 7900 and the 7800. The 8800 triple quadrupole was introduced in 2012. That has now been upgraded to the 8900, and currently today we have 3 instruments available: the single quads, the 7800 and the 7900, and the 8900, and today's presentation will focus on the 8900. There are applications and methods for all of these, but I did want to cover some of the upgrades that we made to the 8800 to increase its sensitivity and lots of the other features, which I will not be able to go into, with the exception that Dr. Casey did mention that the sensitivity has been advanced with the 8900, and basically that has been achieved with a new configuration on the detector. I won't be able to go on beyond that, but I just wanted to mention that with this particular unit, we have phenomenal capabilities for extremely difficult elements like sulfur, phosphorus, and silicon that Dr. Casey did allude to. All of these enhancements that were made to the 8900. Most of them are currently available on our single quadrupole 7900, which itself was only introduced a couple years ago. There are a few additional features that are in gray. The use of multiple different types of cells, cell gases that we can now use on the 8900 that were not available on the 8800. I think with that, I'll simply go on to the next, what is going on here? Particular slide must have been doubled. Excuse me for 1 second. There we go. Okay. Some of you may be wondering what a triple quadrupole ICP-MS is. The IUPAC definition of a triple quadrupole, it is 2 transmission quadrupole mass spectrometers in series with a non-selecting RF quadrupole or other multipole in between them acting as a collision cell. If other manufacturers mention that they have a triple quadrupole, I would remind you to ask them if they actually have a unit mass resolution device on the front end quad. That is really what is the definition of a quadrupole mass spectrometer. With that, what is it different and how does it work? The front end of the instrument is the same plasma as on a single quad SQ. The back end is the detector that is essentially the same as single quad. The selecting quadrupole Q2 here is identical, as well as the cell itself, ORS4. What's different is we actually have a quadrupole in front of the cell. Q1 allows us to control precisely what ions go into the cell. We prefer to use it in a single ion mode, and that allows very consistent reactions to take place within the cell so that we control it very precisely. Trying to hurry. How does it actually work, and what are some of the mechanisms by which it can run? One is an on-mass mode type of measurement. That is where Q1 and Q2 are set at the target mass for the analyte of interest. In this case, we can introduce a reaction gas into the cell that actually promotes the interferent up to a new mass. With this particular configuration, all off-mass interferences are removed from the first quadrupole, so that the only items that enter the cell are the analyte ion itself and any on-mass interferences. If we have a reaction gas that is introduced into the cell that promotes the interference up to a new mass, then Q2, set at the target analyte mass, only sees the analyte. The perfect example of this is silicon in a petrochemical example. Dr. Casey talked about petrochemical and geological, so I've been trying to focus on those particular applications here. And the measurement is silicon using hydrogen as a reaction gas. In this case, with petrochemical samples, you may have a lot of carbon monoxide. Carbon at mass 12, oxygen at 16 produces a polyatomic at 28. Silicon's predominant isotope is at 28. If you tried to measure silicon without a reaction gas, you would have a huge interference from CO. With hydrogen, it reacts with CO and promotes it up to mass 29 as COH. Silicon does not react, and so you're able to identify silicon quite nicely. And here is a calibration curve for silicon on the left in a triple quadrupole instrument, and on the right in a single quad. Again, both of these are with hydrogen, and you can see the graphic on the right shows quite a shift in the single quadrupole instrument. That's predominantly due to CO. If we take a quick look at the figures of merit, the second line down is for a triple quad where Q1 is at 28 and Q2 is at 28, and you can see the detection limits on the far right are about a factor 4 lower than a single quad, even with a collision cell. The BECs, that's the background equivalent concentrations, you see are an order of magnitude lower. So we can see that we can achieve much lower detection levels with a triple quadrupole ICP-MS. For reference, back to our 7700, with diesel and some other heavier organic matrices, you can see that we're 2 orders of magnitude below some of the detection limits that were achieved in those days on that instrument. Another capability of the triple quadrupole is that it can be run in a mode called mass shift mode. In this case, Q1 is set to the mass of the analyte of interest, and Q2 is set to the analyte of interest is now reactive with the gas. Okay, so we're introducing a gas that promotes the analyte of interest up to a new mass, and Q2 is set to the mass of that product ion. Okay, and in this case, an example is, again, an organic example here, and we are mass shifting sulfur. Sulfur, as you probably know, is extremely difficult to measure because it has high ionization potentials, and also because it has lots of polyatomic interferences, and one of them is oxygen. Okay, if we were to try to measure sulfur in a single quad where we have a reaction cell there, yes, we could promote sulfur up to sulfur oxide. But if there's other things in there, for example, carbon from an organic matrix, we could potentially have argon carbide interfering sulfur. And so this is where the results would be in doubt. Okay? On a triple quad, notice down below that argon carbide, calcium at mass 48, and titanium all are removed from the first quadrupole that's set at 32. The only ions that come through from 32 are sulfur at 32 and the oxygen dimer. In the cell, as I showed you earlier, sulfur is not reactive with additional oxygen. I'm sorry, sulfur is reactive, oxygen is not, and so Q2 is set at mass 48 where sulfur oxide is, and it's observed all by itself. Some of the calibration data here. I like to say the proof is in the pudding, and so if we look at mass 48 to 50, we actually see the isotopic abundance of sulfur perfectly matching the natural isotopic abundance of sulfur at his isotopes 32, 34, and 35. That proves that we have removed all kinds of the possible interferences. Here is a calibration curve for sulfur, mass shifted in 20% isopropyl alcohol, and you can see in this organic matrix that in the graph onto the right, or the table onto the right, that we can see as low as 0.1 ppb. For reference, on the 7700, we're actually up in the tens to 100 ppb range for detection limits, so we've been able to improve our detection limits for sulfur by orders of magnitude. If we look at ultra-high purity water on the 8900, we can actually see detection levels that are even below that, and I just exploded this one little region of this to show you that the detection limit for sulfur is 5 parts per trillion. For those of you who have tried to measure sulfur on single quadrupole units, you know that this is unprecedented levels of detection for this extremely high ionization element. Silicon over here on the left side has a DL of 15 ppt, and this is why we can guarantee that we can measure these extremely challenging elements all the way down to 50 parts per trillion. I've given you examples for petrochemical. In fact, high purity water and the alcohol are semicon examples. I'd like to give you just one real quick example of a materials example, and that is rare earth elements in high purity gadolinium, which is used as a contrast agent. Gadolinium interferes with titanium down in the middle of the graph there. I'm sorry, terbium, excuse me, at 159, that's gadolinium hydride. It also interferes with ytterbium up at 172, okay? So if you're trying to measure this with a single quad, even with some collision cell technology, you'd probably still have results that could be in doubt. However, if we use the triple quadrupole ICP-MS, and we look at terbium by mass shifting it, okay, we actually have the ability to measure terbium all the way down to about 20 parts per trillion, and ytterbium by on mass measurement, that is where we end up shifting the analyte of interest, where we shift the interference away from ytterbium, we can measure it all down to 50 parts per trillion. Okay, I've kind of messed up my slides, so I'm going to have to go on. And I believe that was my last slide. I'd just like to say that this unit really creates the potential where results are beyond doubt, okay? It has phenomenal ability to remove polyatomic interferences, even for the most challenging elements such as sulfur, phosphorus, and silicon. I wasn't able to talk about some of the really unique features that have been upgraded on it, like ultra-high matrix introduction for very high salts. It truly is a very exciting and versatile instrument for research and method development. And with that, I'd like to thank you and pass the conversation back on to Laura Bush. Thank you.
Thank you very much. I thank all of you. We're tight on time, so what I want to do is just remind you all that if you'd like to submit a question, you can still do that now. And what we'll do is we'll just answer 1 or 2 questions now, and then we'll answer more after the event is over. We'll get to anyone we didn't answer. So as a quick reminder, you can ask questions by typing them in the Q&A box, which you can find on the right-hand side of your screen. Okay, so here's a question for Giulio. This person says, I have some questions related to the working pressure of the ultra-wave digestion unit. How does the equipment work to increase or reduce pressure, working through the control of the solenoid valve? And the second question is, do we need to install inert gas cylinder next to the, next to the equipment, I think is what it's saying.
Okay, thanks for the question. So the system basically requires a connection to the nitrogen cylinder, either that can stay either close to the unit or a high pressure line that can reach to the lab. So whatever is available in the lab. Regarding how the system builds the pressure, you basically load an initial pressure of between 30 and 50 bar at the beginning of the process, and then you don't need to load additional pressure during the run. Basically, thanks to the heating and thanks to the decomposition of the sample, the pressure is automatically built during the digestion, and therefore the pressure is increasing during the run. So the nitrogen is used only at the beginning of the process.
Fantastic. Okay, let's just do one more then. I think this is for Dr. Casey. What are the key differences between bomb digestion and SRC microwave digestion?
So some of the key differences are the amount of sample we can include in the bomb is much lower. So for example, if we're digesting oils, those oils can only be 0.1 gram in the bomb, but we can go up to 0.6 grams in the microwave digestion. So sample size is really limited in the bombs. That's one factor. The reagent use is less in the microwave system, so we use less reagents in the microwave. And we can go to much higher pressures in the microwave and much higher temperatures in the microwave than we can go in the bomb digestion. So those are all advantages for us in terms of microwave digestion versus bomb digestion.
Fantastic. Well, I think because we're late on time, we should wrap up. But as I said, we'll follow up with with people on their unanswered questions after the event. I'd like to thank all of you in the audience for attending and participating in our event today. And I'd like to thank all of our speakers. And I'd like to thank our sponsor, Milestone, for making today's webcast possible. This webcast will be available for on-demand viewing through October of next year. You'll receive an email from Spectroscopy alerting you when the webcast is available for replay. We invite you to forward that announcement to your colleagues who might have missed today's live event. We hope to see you all next time. Goodbye.